Let's start with today's lesson, which is about internet addresses. So first, I have this Google survey that I'll put into the chat for you guys. And I think last time some of you guys did it at the end, but I think it would be a lot easier if you guys followed along with it and filled out the survey as I go through the slides. It will be a lot easier. So yeah, it's if you see if there's anything wrong, like last time I accidentally put multiple choice instead of short answer, also let me know. You can private chatting me or something and I could fix that pretty quickly. Yeah, so let me know if you have any problems or anything. And I'm going to start with today's slides, which is internet addresses, like I said. So this is a video from last lesson that I want to look at. This is about the underwater cables that we talked about. I think it's a very interesting topic to me, and I want to share this with you guys. So do you guys prefer to watch this on your own? It's really short, it's like 2 minutes. Or do you want me to play it on the screen? Okay, I guess I'll play it on my end. And if you guys can't hear it or anything, also let me know that. Yeah.
They said it couldn't be done. They said.
We never stop hearing about how the internet's in the cloud.
Okay, let me share it with you guys.
We never stop hearing about how the internet's in the cloud, but really, it's in the ocean. About 300 undersea fiber optic cables are responsible for 99% of international data traffic. It's basically the same way we connect to each other in a single country, except underwater instead of underground. They transmit PewDiePie from Europe to America, and they connect stock traders in New York and London. And these cables, placed by private companies, are the backbone of the internet. But if you held one in your hand, it'd be no bigger than a soda can. There are just a few layers of protection from the water, including petroleum jelly. Yes, your internet is covered in Vaseline. They're vulnerable to earthquakes. At least a few times, confused sharks have bitten them. But many cables are beneath sea life because in some places they go as deep underwater as Mount Everest is high. Ships lower a plow that digs a tiny groove in the ocean floor, lay in the cable, and it's naturally buried by sand thanks to the ocean's current. And that process, it's both stunningly simple and mind-blowingly complex, is responsible for making the internet a truly global network. It's an idea that's audacious and crazy, and you think it has to be cutting edge, and it is, but it's also been going on for 157 years. Electric telegraphs have been around for a long time. Experiments in the early 1800s connected two ends of a garden using a clock that revealed letters. Then they moved on to two neighborhoods to help signal trains, and then multiple cities thanks to a network of railroad lines. Underwater submarine cables were an obvious next step, so they played around. Instead of petroleum jelly, the first ones were coated with exotic tree sap to protect them from the water. And though the undersea cables came in spurts, one of the first ones was knocked out of commission by a fishing boat. By 1858, they reached around the Atlantic and across the world. And that's how it's kind of gone since, laying cables that circle the Earth's oceans. The cables are unwound from the back of the ship, sink to the ocean floor, and the world is connected in speeds measured in milliseconds. There are ideas to bring the internet above sea level. Along with cell phone towers, there's internet beamed from Facebook satellites to Africa and balloons lifted by Google. But for speedy international travel, undersea cables are still where companies like Facebook and Google place their bets. That's because the best way to create the cloud is still by going under the sea.
Okay, hopefully that video gave you a little bit more interesting information about what's going on currently with the world and with the internet. And yeah, just more information about how these underwater cables work. Okay, let's go back to the slides now. So What we learned last week was about transmitting digital information through like electricity, through light, through all of that. So, okay, today we're going to be focusing on another part of that, which is like exactly how two computers are able to locate each other through the internet. So this is more of like the router way, or like the radio cell tower function, because there's no two cables that are directly connecting two computers. Okay, so this is what we call internet addresses, because just like how we have our addresses for like each location, our houses, our mail, computers also have addresses that make each one of them unique. So yeah, every device has a unique address that refers only to that, and it can be found by any other device looking for it. So in a way, in a funny way, these devices are even more unique than our names, because there's no way that it can be repeated. Okay, so let's start with the example of a normal address, a mailing address. So this is the address of the happiest place on earth, Disneyland, probably somewhere we all wish to be right now. So as you look at this, from here, there's the country, and then there's the state, which is like the next level, and then the county, and the road it's in, and it's a specific number, it's suite. So as when we read the address, it goes from, if you start here, it goes from more general, less general, and then it goes all the way to the most specific, where you could like locate the Disneyland Resort with just one like street address, and you don't necessarily need all the other stuff. But with computers, it's similar but also different, because yes, it goes from most general to least general, most specific, but it's not in a way that we humans read it with letters. It's as you probably would guess, it's transmitted through numbers. Okay, so internet addresses. Every single device on the internet has a unique one, like we said. And anytime information is sent over the internet, it has both a to and a from address. And later we're going to be learning more about that too, like how exactly is information sent, and like how this to and from address is contained in, well, like packaged in a way. So internet addresses follow Internet Protocol, or also known as IP. And this defines the layout of these internet addresses. And in this case, we can also call them IP addresses. And this is something that you might be familiar with. It's a pretty common term, especially if you look like sci-fi movies and they're like, oh, we traced the signal back to this IP address, and that is referring to like this specific number given to your a laptop or a device. So yeah, that's how they track down a hacker or anything. And again, like I said, protocol, to remind you of that, is it's just like a standard in which all of a standardized way the internet works, because otherwise computers wouldn't be able to communicate with each other. Okay, so this is an example of an IP address, or one type of IP address, I should say. So we're going to look at what each of these numbers or sections of numbers represent, and how they are kind of like our mailing addresses. Okay, like a mailing address, we go piece by piece and hone in on a specific location, with each piece offering increasing specificity. So starting from the first one, we have 93, which is we would locate the specific network, and later there will be like a visualization for you guys to see exactly how this works. So this first one is the network. Second one is the subnetwork. Third one is the sub-subnetwork, which I know is a weird name, but that's what we call it. And the last one is the device. So this is divided into 4 clusters, and the first and last cluster has 2 numbers, and the 2 clusters in between have 3 numbers. So this is how we would use this. Okay, so now for a visualization. I also want to point out that this is different than a mailing address, because usually we read from right to left. So like, sorry, left to right. And so so we start from the most specific one, which is like the street name, and then like the last one we would list would be like the country, the most specific, the most general parts. And over here, it's the other way around, so it's flipped. So we start from the most general and then go more specific. But if you think of it this way, it kind of makes more sense how the computer is doing it, because we want to narrow it down one by one. So if you look at this, the computer reads in the 93. So it's going to go on this branch, which is the internet, and it's going to look for branch number 93, or however they read it, which is going to be narrowed down to this one. Next is they read the 184, and then again within the broader network, it looks for this subnetwork, and it's like matched in pink. You can tell we narrowed it down here. And then finally, this is like this blue color. Is the sub network, which is 216, and it's these 2 nodes right here. And lastly, we read in the device number, and it's this dot right here. Of course, the internet, it's going to be more complex than this. There'll be more branches, but this is like a really general idea of what we're trying to do here. Okay, so how do we represent these numbers? Because this is still what we as people read. So we're going to try to switch it to binary. If you guys remember from last class, binary is usually it's the most common way in which computers deal with information, well, any type of information, including text, including images and other files. So we're going to translate this decimal into binary. So as you see here with the very long list of binary numbers, this is the equivalent as each of these. So 93 is equivalent to this, and so on. And each of these, each number within the address can be represented by 8 bits. So 1, 2, 3, 4, 5, 6, 7, 8. And the largest number for any given spot is 255, because it's 2 to the 8th power, and then you don't count the last one. So 255. Okay, so if we get rid of the periods and spaces, because once again, this is what we humans want to look at for simplicity, we were left with a 32-bit binary number. So this is what the computer deals with. So the computer will look at these 8 numbers and then segment it itself. Given a 32-bit number, we can have a maximum of 2 to the power of 32 total different IP addresses, which is over 4 billion. So there's over 4 billion different IP addresses, which may seem like a lot, but again, later we're going to learn that as the internet expands, 4 billion is actually not a lot, because think about how many devices you have at home and how many devices you don't use anymore. So sorry, I'm getting ahead of myself. So this 32-bit version of IP addresses, or you can call it IPv4, it has been around since the 80s, the 1980s. So basically, we call it IPv4 because, as you can see here, there's 4 clusters, so that makes sense. So as the internet grew, it became more popular than we expected. It became apparent that 4 billion unique addresses isn't going to be enough. So a new protocol is being put in place to accommodate for this. And this new protocol, like I mentioned, is IPv6. IPv6 is the new standard for internet addresses. Yes, and it's actively being swapped for IPv4. And like we learned in IPv4, there's 4 clusters and everything is in binary, and it's 32 bits. But in IPv6, each device has an address that consists of 8 4-bit hexadecimals. So like we learned yesterday, sorry, not yesterday, last week, hexadecimals is another way to write numbers essentially. And the good thing about this is that we can represent more numbers in less places. So like 10 might take up 2 places, but in 10 in hexadecimal, it would only take up 1, which is good because we want that. And I also want to mention that this IPv6 process is also related to scalability, which is like a term that we often deal with because we want the internet to be scalable. And in the previous IPv4 format, it was not scalable because the maximum we could add is 4 billion devices. But with IPv6, we kind of future-proofed it a little. I don't, like, in my opinion, why not just do more? But yeah. But it has, and here we're going to learn exactly how much we improved it by. So this is an example of a IPv6 IP address. So if we remember how many bits we can use to represent hexadecimal digits, we can calculate the total number of bits in one IPv6 address. So here we have 8 clusters, 1, 2, 3, 4, 5, 6, 7, 8. We have 4 digits per cluster over here, and we have 4 bits per digit. And this would equal to 128 bits in total. But then we do 2 to the power of 128 because each place, it could be either 1 or 2. So we do that, and then we come up with this really big number. That's the maximum amount of devices that can connect to the internet. Yeah, so this translating process, it's still ongoing because again, it's really difficult to like transfer all these devices at once. So what the people who make these decisions have to do is take all of the 4 billion devices which were previously in IPv4 and then like switch them, like convert them from binary to hexadecimal and then reassign the other ones. So yeah, it's quite a bit of work and it's again an ongoing process. Okay, so we're gonna look at who exactly decides this stuff because the internet is so open sourced. We don't really know sometimes who's in charge of it. So the people who decided this was International Engineering Task Force, or IETF, and they're responsible for making these decisions. And if you want to we're going to take a look at their website later, but yeah, this is their official website. They're a open community of engineers, designers, vendors, and researchers concerned with the evolution and smooth functioning of the internet. They're also all volunteers for that position they hold. So if this is like something you want to like learn more about or something that you want to participate in, you can definitely ask them. Maybe look on their website and see if you can sign up as a volunteer or something. I haven't looked, so I don't know too much about that. But yeah, we're going to take the time now to 10 to 15 minutes to take a look at their website and see see what you can find. So there's 3 main sectors that I gathered from their website. First is the automated network management, which their goal is to efficiently manage a larger and more complex internet. So again, the scalability and the reliability of the internet. Next, they call it the new transport technology, which focuses on sending information over the internet. And next one is security and privacy. And this is very important. They try to create a trusted internet. Yeah, so I'm going to put these links into the chat. Sorry. I'm going to put these links into the chat, and then you can take a few minutes to look at this. Yeah, that should be enough time for you guys. Does anyone need more time? Okay, let's move on then. So, some of you guys requested to, in the first class, to go over who invented the internet and the history of the internet. So, we're going to talk about a little about that here. So, the short answer to who invented the internet is actually a bunch of people. There isn't a specific person that was credited with the development of internet, but yeah, many people had played a part in it. So starting from the earliest in the early 1900s, Nikola Tesla, he toyed with the idea of a world wireless system, which is pretty close to what we have today, except it's, yeah, it's our internet is not wireless, of course. And then in the 1930s and 1940s, we have mechanized searchable storage systems of books and media, and that was developed. So you could think of this as like ebooks or like ordering e-files and such stuff like that. And in the early 1960s, MIT's Licklider, I think, I'm not sure how to pronounce that. He popularized intergalactic network of computers. And of course, intergalactic network, it's obviously not what we have today, but I think the fact that people thought the internet was plausible and not just not just science fiction, that was very important during this time. And lastly, packet switching also made transmitting electric data more efficient. So we're going to learn about packets later, and you'll know what that is. And okay, so a bit of a history lesson here, but in the 1930s and 1940s, that was around the start of World War II, but like and in the 1920s, a lot of inventions were like made, like radios were discovered in 1920, and also cars were made in the 1920s. So it only made sense that from there everything would become more digital. And in the 1960s, it would make sense that people wanted at least the hope of a better science system, because this was during the Cold War when US was fighting against Soviet Union, and then yeah, it was a very like startling concept. It was like a goal to work towards. Okay, so the first workable prototype was in the late 1960s, like I said, during World War II, with the creation of ARPANET. I don't know how to pronounce that either, but it stands for Advanced Research Projects Agency Network. So this was funded by the Department of Defense, so it's part of the US government. And this was, I guess, yeah, just so the first computer communication that was made was between a lab at UCLA and to a lab in Stanford. So it's not a very long distance because Stanford's like not that far away. They're in the same state at least, but Stanford only received the first 2 letters, the note of the entire note, which isn't the results that we did today. Imagine if you like received an email today and you only saw like the first word hi or something. It wouldn't be really useful, but what this demonstrated was that this was a possible theory that people could work on, and it was a potential for the future, which it is because it happened. Okay, and then in the 1970s, Robert Kahn and Vinton Cerf. Sorry, I'm like told I don't know these names right. I don't know how to pronounce these names. They developed TCP, which stands for Transmission Control Protocol, and IP. So we're going to learn about TCP later, but it's also part of packet switching. And IP, we just learned about, IP addresses. And on January 1st of 1983, ARPANET began to assemble the network of networks as we know today. So this would mean that they started connecting routers together. They started, and basically we could start recognizing it for what the modern internet is. So they started making the internet technically. And in 1990, Tim Berners-Lee invented the World Wide Web, WWW, and it's the most recognizable form today. So in the last 20 years, in the last 20, 30 years, technology has been growing pretty exponentially, and then the internet was definitely a very significant start to that. Let's play a video. This will give you like a bit of a review and also a bit of a preview of what we learned so far.
So, how does the internet work? Most of us know how to use the internet without actually understanding how it works, sort of like electricity in your home. You use it every day, but may not understand the mechanics behind it. And if the electric grid is difficult to understand, then the internet must be impossible, right? Wrong. In the next few minutes, I'll put you in the top 10% of people who understand how the internet actually works. For SecurityCatalyst.com, I'm Aaron Titus. Whenever most people think of the internet, this is what comes to mind. The internet is not a bubble cloud, even in the new age of cloud computing. The whole fuzzy cloud picture was created by people more concerned about job security than education. This is the internet. The internet is a wire, actually buried in the ground. It might be fiber optics, copper, or occasionally beamed to satellites or through cell phone networks, but the internet is simply a wire. The internet is useful because 2 computers connected directly to this wire can communicate. A server is a special computer connected directly to the internet, and web pages are files on that server's hard drive. Every server has a unique Internet Protocol address, or IP address. Just like a postal address, IP addresses help computers find each other. But since 72.14.205.100 doesn't exactly roll off the tongue, we also give them names like Google.com, Facebook.com, or SecurityCatalyst.com. So this is how it works. Your computer at home is not a server, because it's not connected directly to the internet. Computers you and I use every day are called clients, because they're connected indirectly to the internet through an internet service provider. Here we'll pretend that this is my home laptop and I'm using DSL. Now let's pretend that I want to visit AOL.com, which is coincidentally both a server and an ISP. I hop onto my laptop with DSL, go through my ISP, onto the internet, and look at AOL.com. My computer connects with AOL.com, and I can look at its web pages. Now, let's say that I want to send an email to Aunt Ruth. Aunt Ruth has AOL dial-up from home, and I've got a Gmail account. I log on to gmail.com and compose a message to Aunt Ruth's email address, auntruth@aol.com. Once I click send, gmail.com sends the email to AOL.com. The next day, Aunt Ruth dials into AOL servers and retrieves the email. Whenever an email, picture, or web page travels across the internet, Computers break the information into smaller pieces called packets.
And this will also be what we're going to be learning later. So that's a little preview.
When information reaches its destination, the packets are reassembled in their original order to make a picture, email, web page, or tweet. Okay, so imagine you're at work sitting next to your boss, and you're both surfing online. Your boss is doing market research, and you're updating your Facebook profile. You're both sending packets back and forth over the internet. But what's to keep your packets from accidentally ending up on your boss's screen? That could be embarrassing. The solution to that problem is IP addresses and routers. Everything connected directly or indirectly to the internet has an IP address. Everything. That includes your computer, servers, cell phones, and all of the equipment in between. Anywhere two or more parts of the internet intersect, there's a piece of equipment called a router. Routers direct your packets around the internet, helping each packet get one step closer to its destination. Every time.
And routers are what we learned about last time, and it's how they connect the network of networks.
You visit a website, upwards of 10 to 15 routers may help your packets find their way to and from your computer. Imagine each packet as a piece of candy wrapped in several layers. The first layer is your computer's IP address. Your computer sends the packet to the first router, which adds its own IP address. Each time the packet reaches a new router, another layer is added until it reaches the server. Then, when the server sends back information, it creates packets with an identical wrapping. As the packet makes its way over the internet back to your computer, each router unwraps a layer to discover where to send the packet next until it reaches your computer and not your boss's. And that's how the internet works, in 5 minutes or less. And you're now easily in the top 10% of people who understand the basics of the internet. If you found this video helpful, check out securitycatalyst.com for all kinds of ideas on how to protect your information.
Okay, so I want to come back to this part for a minute. So as you can see, they kind of correlate a IP address or a router with a name, a human readable website name. And this is what we call the domain naming system. And that's what we're going to be learning about next week. Let's keep going. So, like I said, the domain name system will be what we're learning next, because IP addresses, they're not very human readable. So we need a system that translates between the human readable names and the machine readable IP addresses. So, let's go back to the idea of routing. And routing is the process of sending data between two computers on the internet. The data is sent through routers that determine the route. So when it sends the route, it's going to take in several different factors and decide what the best route is. And you might be asking, oh, like, how do they know whether it's which route to take? And this is what we're going to be looking at next. This is a bit of like an interactive example that can help you visualize what routing is. Okay, so this is like a assignments list that I used to use. And over here in the introduction, it says that before you send a request to a particular IP address, that request is sent through the vast network of routers before it reaches its final destination. Each router is connected to several other routers. When one router receives a request, it computes the costs of forwarding the next, and it chooses the route with the lowest cost. And cost in this context doesn't really refer to money, but it could instead refer to things like the distance between the IP address to the final destination and the trustworthiness of the router. So because routers are like constantly removed and added to the network, you can see your requests take different paths over time. So the router for this website is located in Oregon, and you're going to see most of the paths start that way. And then we're going to look at how they send requests. So basically, let's say we want to send one from this website to google.com. And we click go. That was a little fast, but you could see where it went, right? It went like pretty different places. And I think that's really interesting because it's evaluating not necessarily the distance between two places, but the cost of between the routes. And if we were to send one to the White House, this would be the route that it would take. And over here, these are IP addresses, and these are IPv4, so they're like older ones. And let's say we were to send it to MIT. Let's see which path the routers would take. Okay, so it would take a router path, which a longer path, which makes sense because Oregon's pretty far from Massachusetts. So now that you know what routing kind of looks like, let's go back to the other PowerPoint. Okay, so like we said before, one computer can send a message to another through a simple router. So in this example, this computer on the left that says whose IP address is 2.2.2.2, it writes a message and then it marks it with a to and from address, just like the postal mail. So it's gonna mark a message and then it's gonna say I'm sending it from me all the way to this computer on the right here, which is 9.9.9.9. And then it's gonna travel through this entire network of routers until it reaches there. So again, there's the cost is referring to different factors when computing routing, such as the closeness of an IP address, the trustworthiness of a router, or the speed of a connection. So yeah, they're just different examples that the system takes into account too. And then here we have the example I was stating, to, from, to, and then you have the message, which let's say hypothetically it's hey. We just did that example. So the computer on the left, and here we have the actual message. It's going to pass through all these systems, these routers, sorry. And here is one path that you could take from here to here, here, and here, and here, which is in blue. And then here, 9.9.9, let's say that he receives this message. So now that the other computer has received the message, it can compose its response. And in a similar fashion, it's going to say from, which is 9.9.9, to 2.2.2.2, and the message it's going to reply to hey is oi. So that computer that then sends its message back using the same process, the same packet process. Okay, and at this point, let's go back to like a vocab word that we learned previously, which is redundancy. So notice that the message sent to and from each computer went in a completely different path each time, which, and that's the great thing about the way internet is structured, is that there's plenty of redundancy and there are many ways for information to travel between two devices. If we go back to here, let me show you this example. If we go back here, this is the path that it chose to take from here to here, all the way back. But you can also see, like, you can go here, you can go here, here. There's just many ways that you can take. So for example, if one router failed, the message would still be able to make it across the internet, and that's redundancy. Okay, so the dictionary definition for redundancy is redundancy in terms of technology. The dictionary definition of that is the inclusion of extra components which are not strictly necessary to functioning in case of a failure in other components. It improves the overall reliability of the system. The system is also fault tolerant, which is part of redundancy, which means that backup components automatically take the place of failed components, ensuring that there's no loss of service. Because the most important thing to the internet service providers or ISP such as AT&T, Comcast is that the overall system works and there's nothing wrong with it. So otherwise they like the financial factor of that would be like they lose clients or they like don't necessarily do as well. Yeah. So if we look at this is what I was talking about before, but if we look at this path, we can see that's one of many potential paths the data could take from one computer to another. If a router were to fail or to break, we could find another way to get our information where it needs to go. So if this hypothetical router broke, then instead of this path that won't work anymore, we could take another path here, 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 here. Yeah, there's still, in this case, 3 other paths we could take, but usually in the internet, because there's more routers, there's more paths we can take. Yeah, so let's say again, if this router failed over here and also these 2 routers both failed. However, there is still a way for the message, for the packet to go through. You just have to go another way. Yeah. So pretty much what's the saying is that even though there can be routers that fail, overall most of the time we can still send the message that we want. And sorry, when I say when a router has failed, they can be overloaded because there's too many requests going through, or they could it's simply removed because that company doesn't provide service anymore or anything like that. So, and this applying to the internet is that if an individual router breaks, and they often do, the whole internet doesn't grind to a halt. And that's good because we want to be able to use the internet all the time. So the routing system is also very scalable. And we've seen this word a lot in terms of good things about the internet, because we want to future-proof our system and ensure that the internet will continue to run smoothly as it increases in size. So going back to the IP addresses, if all the addresses in IPv6 were filled, the internet should still be able to work as good as it does now. So it's a good thing that the internet is scalable. But unlike the more unique thing about the internet is that unlike many things, when we add more routers, meaning that when we increase the load of the internet, we get a better performance because of redundancy. So if you add more routers, there's more path that the message can potentially take to get to the other client that we want to communicate with. And yeah, it just takes the pressure off of other systems. Now we're going to look at exactly, yeah, you could, and there's an example in the chat. Now we're going to look at how data is transmitted, because, here, let me go back. Because we've looked at how data is transmitted, which is through the light, radio, and electricity, but those are like pretty simple ways of transmitting data. It's what we rely on, but for more efficient ways, like if you're sending a picture or if you're sending a video, you have to find another way to transmit the data more efficiently. So what would our messages look like if we were to do that? So now that we have a good idea of how our messages are sent from one end of the internet to another, we're going to get a better idea of what the contents of each message looks like. So this is the time when we introduce packets. So anytime data is sent over the internet, it can be broken down to small units of data called packets. And these packets are made up of binary bits and such as that. So the reason we do this is to ensure that our data can transfer nicely. It's easier to transfer a small piece than one whole. So for example, if you built a house in Minnesota where it's cheaper and you want to move that house to California, you wouldn't necessarily want to move the entire house on the truck and move it all at once. Or even when you're like packing and stuff, you usually put it in smaller boxes and then move each part individually with like a truck or a plane or whatever. Yeah, so like and each of these paths and each of these pieces could even take its own path to get to its final destination, just like the packets on the internet. And okay, you've probably seen this in the video, but this is what the concept we're going to go over again. So if we want to send this very cute cat picture over the internet, we'll break it down to packets. So in this example, we sliced this picture into 4s, and there's this one packet has now been broken down into 4. So in this section, each packet will be visualized by envelopes, and you can see each cat has its own envelope. And each of those packets is labeled with metadata. And metadata means data about the data inside of them. I know it's kind of tricky, but here, these are all metadata. So to, from, size, and the size, these are all different types of metadata because it's describing the data inside of them. And the actual data, of course, would just be like 0s and 1s, or in this in this case, the picture of the cat's tail. So, another example of metadata would be like if you have a, let's think of one. Let's say you have like a data set of people who have went fishing in the past year. So, data describing metadata for that could be like, when was like, what was like, when do you define as the past year, how many people you surveyed, what's like the area of people you surveyed, and the actual data, of course, would just be the number of people who did go fishing the previous year. So once these packets arrive on the other end of the once these packets arrive on the other end, meaning they reach the target computer through IP addresses, they can be reassembled into an image, and the layout of the packet is defined by protocol. And again, this protocol is also the Internet Protocol, or IP. So this is of course familiar because we just learned about this, and it's basically you use the same protocol for both of these components, which is really cool and efficient. So this is the standard layout for every package using IP. First, you have a destination, you have a from, so you have the to and from, the actual data being transmitted. And this is pretty straightforward. It's the easiest way to do it. And in that previous slide, like way back to when we were talking about routing, and that text box, that would be an example of IP, like sending information through IP. So right here. So let's go back. Okay. And of course, number 1 and number 2 are considered metadata because they're data about the actual information packets. The internet gives each device an address and defines the layout of a single packet for 2 computers on a network to send single packets to each other. But let's think about it. But it works for one packet, but what if there's like multiple packets? So here we need to use another protocol, which is TCP, or a transfer control protocol that allows for multiple packets to be sent between computers. And you would remember TCP from our history of the internet lesson. So yeah, so this was invented the same time that IP was invented. So basically what TCP will do is that they will check that all packets have arrived and that, oops, there's two that's, have arrived and that they're able to reassemble in proper order. Okay, so each of these packets is labeled with, again, they're also, sorry, for IP packets, they're labeled with metadata. But for TCP packets, the difference is that they will add a packet number to each of these packets so we can keep track of the order and quantity. So for example, this tail part section would be 1 out of the 4 packets. This hind legs would be 2 out of 4, front leg 3 out of 4, and the head 4 out of 4. So when the computer receives these packets, they can like double check to make sure that all 4 are there using the TCP protocol, TCP packets, right? If the packets happen to arrive in the wrong order, then like this metadata will allow them to be pieced back together correctly. But if one of the packets is missing entirely, TCP will re-request that entire packet. So once all the packets arrive, they can be reassembled in the correct order. Once again using that metadata packet labeling. And now we're going to look into like how exactly TCP will re-request that packet. So to summarize, these are like the 4 things that are possible. The four metadata that can be used by TCP and IP. And what's special is that TCP will contain the order number while IP doesn't. And both IP and TCP will contain the first 3, which is destination, from, and the size of the message. So next, we're going to talk about the protocol and that dictates how the data within the packets will actually be stored. So we previously talked about metadata, and this will just be the actual data. And this, we call it the Hypertext Transfer Protocol, or HTTP. So this might be familiar because you probably heard it from the language HTML. And this is kind of similar because it's the coding language to build websites, and this is the protocol that transfers data. So this protocol standardizes the language that computers use to talk to web servers, as well as receiving web resources. This is the system that all computers use, so you won't have any errors there. And it standardizes communication between devices and how web resources are transmitted. HTTP also defines how computers request and receive hypertext information. So again, this protocol has multiple functions within, just like IP, and in order to make this whole process work. And HTML, the coding language HTML is used to build websites, and that's pretty, that matches up with this because this also uses, HTTP, the protocol uses this language to talk to web resources. So let's look at exactly how the request and response would work. So when we're sending a message to a server asking for a web resource, there's a request and a response. That's how IP packets work too. So once the request is received by the server, then the program reads it and it determines how to respond. So for example, we have here, this message is get homepage.html, HTTP 1.1. Its host is like example.com. The content type, we know it's going to be text-based and HTML, and the language is going to be in English. And here we have 200, and so basically we're going to send this request, and this is the response part, and we're going to look at that later. So all the protocols and systems work in tandem to send messages from one device to the other. So TCP, IP, DNS, which is domain naming system that we'll learn next week, and routing all work together to send packets over the internet, and HTTP makes sure that the information within those packets can be understood on both sides. So together, they basically make the internet function. And since all computers connected to the internet follow the same rules, communication is standardized across devices. So this makes the transmission of data from one computer to another very simple, which is good, something we want. And we looked at this video, and we're just going to look at this introductory video about DNS.
To identify each other on the internet. As we can't always remember complicated numbers, we use words instead. The domain name system brings the two together to get you to your destination. This is how it works. All around us we see domain names. For example, the website of your favorite band. The site is stored somewhere on the internet. Let me explain how your PC finds it within milliseconds. The journey starts with typing in the website address. In words, of course, as you wouldn't have remembered IP 88.151.243.8. Your device will read the address backwards. It will start at the end with the root domain, in our case, .eu. Information on the root domains is stored in 13 different root servers located around the world. In reality, there are numerous more copies of each of these machines in different locations to make sure that whatever happens, the system will keep on working. A root server contains the information on the name servers for the different zones. In our case, it tells us where we can find the information on addresses ending with .eu. Again, for reasons of security, there are a number of these .eu name servers located around the world, so that if one is too busy or stops working, for example, due to an earthquake, the information would still be reachable elsewhere. The .eu name server knows where the information for the more than 3 million .eu addresses is stored, and will tell us where we can find flamingflamingos.eu. It will communicate this unique IP address. The IP address for the Flaming Flamingos website is now identified and sent to your computer. Now the download of the content can start. But remember, this whole process that makes it possible to connect your computer to the place where the website is stored happens in just a few milliseconds before it connects to the internet and starts downloading the information. In reality, a lot of information is stored along the road in the so-called cache memories, so that the information can be retrieved faster than having to return to the root every time.
Okay. Yeah, I really like how he mentioned cache. So basically, cache is basically your local computer memory file, and if you already visited a website before, then that would automatically go into the cache, and then you would have your you would retrieve that website faster. Okay, so let's put all of these systems together and then see what happens when one tries to view a web page. So first we have this, we try to view a website with a URL from that page. Here we have the domain, which is where on the internet you need to look for this, and the path, which is what resource is being requested. It's using the HTML language. And URL, if you never knew, stands for Uniform Resource Locator, because we're locating a resource that exists somewhere on the internet we don't know. But we'll get into the specifics of DNS next week. So next we create this HTTP request. So since our browser knows which URL we want to visit, it'll construct a HTTP request to fit those needs. So here, like we said, we want to get this pathway. The host is this website. Again, context type, context language, English, and so on. So we use DNS to find the IP address. So if we don't have the IP address in our cache, we're going to use DNS. And like for now, we can skip over this and we'll learn more about it next week. Step 4, we use TCP or IP to break the requests into packets. And then this is where we send the actual data and the metadata that goes with it. So here we have the several packets and each of their metadata. And we have, again, these packet numbers, which are unique to TCP. It travels across the internet and it transmits, and it goes through all these routers to get to the final destination. So it's going from 9.9.9.9 to 5.5.5.5, which is example.com. So for example, if we were to go on example.com and say like, I want this web page, we click on their notifications tab, they'll like, and this is the request that we're sending to them. So if any of the packets get lost along the way, again, TCP will go back and re-request that packet. So our step 6 is if the original request is constructed from the packet. So once the recipient has received all the parts, they can put them together in order, like 1, 2, 3, and then you can find basically the request. And the next step would be to create a response that goes back. So after the server reads a request, it will compile any resources that are requested and create an HTTP response to send back. So this will include a status code. So you might be pretty familiar with 404, which stands for error, and then 200 stands for OK, which I thought was pretty cool. And the actual HTML file is also included in the response. So the actual web page is also included. And step 8, just like when the request was sent, the response also needs to be broken down into packets. So again, we have all these packets that it's broken down, that's to be sent back to be sent to our computer 9.9.9.9 from example.com 5.5.5.5. And again, each packet is routed through the internet, maybe through different paths, but we don't know. And the last step is the response is reassembled from the packets. And they're able to reassemble and communicate because servers and computers are using the exact same protocols like IP, TCP, and such as that. So yeah, and from this, our computer can load whatever website it needs. It could be like a simple web page, or it could be like a specific text file that we ordered. And yeah, and basically that's how we view websites. And this all happens within milliseconds. So these 10 responses and even like re-requests, they all happen in a very short amount of time, which is pretty amazing. Yeah, and oh, sorry, this is the last step. The web page is rendered. Yeah, our local using the different computings, our local computer would display that web page on our screen. Okay, to summarize today, we have internet is a system of routers, also a network of networks through which digital data is sent by breaking it down into blocks of bits called packets. And each packet contains both the data being transmitted and the metadata that helps route the information based on cost. And the whole process works because each machine is connected to the internet uses the same protocols for creating, sending, and reading these packets, which includes TCP, IP, and HTTP. And that's the end of our lesson for today. And we finished pretty early today, which is fine. So as long as you finish that survey and you submit it, you are free to go because there's less people, we took less time. Yeah, let me know if you have any last questions or if you want to stay behind and talk.